Hello everyone, today's lecture is on chemical kinetics and chemical equilibrium. First, chemical kinetics. The chemical kinetics is usually used to study the reaction rate and what are all the mechanisms involved in it. Uh, uh, by using this reaction kinetics only, one can control the reaction, and if the variation in conditions may occur, how the reactions vary will be studied. It not only studies by using this chemical kinetics, we not only determining the speed or the rate of the reaction, also it describes the condition where the reaction rate is altered, that is by varying or by changing the conditions like varying the concentrations, temperature and pressure. How the reaction variation occurs are also studied through this chemical kinetics. And usually in the chemical kinetics, for example, any of the reaction, that is the in any chemical reaction, if the reactant that produces the product formation, here we considering that is the 1 mole of reactant R produces 1 mole of the product P. And also in some cases, that is it is if time t1, this product or reactant R1 forms the product P1, whereas at time 2 this reactant 2 forms the product P2. So in order to determine the rate, here the del R of the reactant is the concentration of R1 minus R2, whereas the change in the product is P2 minus P1. Like the way, and this each square bracket indicates the molar concentration of the reactant as well as the product. And the variation in the time, that is T2 minus T1, is known as the del T1. And here always the reactant got decomposed or disappear, whereas the product that is formed, so always the reactant rate is expressed in -1, whereas the product one is in the positive one. That is, for example, we considered the reactant A plus B form C plus D. Here we are going to write the reactant rate means this R and B got decreased. That is, the initial A and B concentration got decreased, thereby the product C and D is formed. So here the slope value is negative, and always the reactant rate will call it as average reaction rate, whereas here it is called it as instantaneous rate. This is mainly due to here we cannot predict how much quantity of the reactant is needed to produce this quantity of the product. So this one is the -1. So always the reactant rate was expressed in terms of negative value. And here the product formation at time increases, the formation of product got increases. So always here the reaction rate is in positive, and the slope value is also positive, that is the dP by dt is positive. Here it is negative. And based on this reaction rate, one can explain order of the reactant too, and also how here the rate can be expressed. That is, if any of the reactant A and B produces the product C and D, then the reaction is like, we need to express the reaction rate as proportional to molar concentration of A and B to the power of their stoichiometric coefficients. And equating this, we included the proportionality constant or the rate constant K. And the order of the reaction is based on the sum of the power of the concentration of the reactant in the rate law is called as the order of the reaction. That is, if here the rate is equal to K is equal to molar concentration of A and B to the power of X and Y, means order is equal to the power of this X and Y is known as the order of the reaction. And again, based on this order value, we may again classify into 0, first and second order reactions. Now coming to the zero order reaction, usually the rate of the reaction here is proportional to 0th power of the order of the reactant. That is, here we consider this, that is R is used to form the product A. So here there is no stoichiometric coefficient, and the order is again 0. So we write this value dr by dt is equal to k into r to the power of 0. So we get the equation of dr by dt is equal to kr. Again, if we express, we integrating this, then dr by r is equal to k into dt. This one is 0 to t, and it may be r naught to r, the reactant value. Then we get the equation value of ln r by r naught is equal to kt plus I is the integration constant. And here again, we may antilog it. R by r naught is equal to e power kt plus I, or r is equal to r naught into e power kt. This is the zero order expression for the rate. Whereas usually this zero order reaction is uncommon. This one is usually occurs in the special conditions. For example, enzyme catalyzed reaction, or the reactions that were occur on the surface of the metal. For example, the decomposition of ammonia occurs on the hot platinum surfaces, and the example